All right, welcome to Physics 2425, Lecture 12. This is rigid body rotation. So we're starting in here into a few sections where we are taking a look at basically everything we did in linear motion, but now we are going to be working in rotational motion. So the first thing we're going to do in this lesson, we're going to take a look at the center of mass because we can no longer treat our objects as point masses, and then start looking at the kinematics of rotational motion. So when you think of what's going on with a point mass, you just treat the object, whatever it was, whether it was a box and it's moving in some direction. It doesn't matter that it's a box. I can just treat it as a point, and all of its mass is the point, and then it's moving in a straight line. The problem is when we start looking at objects that are able to rotate, every part of the object is doing something slightly different. So if you look at like this bat that's being tossed up in the air, if you look at the end of the bat goes through one set of motion. So you can see, you can trace what's going on with the end of the bat. And then at the same time, the other end of the bat is going through a completely different set of motions. You can see that the opposite end of the bat does not move as far. So if you were to trace the motion of the end of the bat, it would go through generally kind of like this parabola type shape here. But the shape that's gone through with the other part of the bat, similar, but definitely doesn't go through the same position change. So what they kind of figured out is that if you average essentially all of the motions together for all of the different points, you can describe the motion of the object based on what happens to the center of mass. So if you look at the center of mass of this bat, which is generally not going to be in the center of the object because this end of the bat is really thin, this side's fatter, so it's going to be a little closer to the other end of the bat. But if you trace that motion, that represents the average motion of the whole object. So we have this idea of the center of mass. So we can have a position of the center of mass. We might call that XCM. We might have a velocity of the center of mass or the acceleration of the center of mass. So we can start describing kinematic variables for the center of mass. And then if we wanted to look specifically at what's going on at a different point, it's generally going to be related to one of the quantities for the center of mass, and basically related based on distance. So we usually use R to be kind of like the radius, how far away from that center are you? So one of the things we have to look at first is this idea of potential energy. So one type of problem that comes up frequently when we start looking at what we call extended bodies. So an extended body is an object that you cannot easily or reasonably treat like a point mass, so an extended body. Picture a rod that has a pivot point. So I've got a pivot point right here, some sort of hinge, and I have a rod here. And let's say that this is an XY plane. So we have the ground here, so that the rod is parallel to the ground. And let's say that I release it from rest so that the rod can swing freely. And I want to describe energy with something along the lines here. Between position 1, which is the horizontal version, and position 2, which is the vertical version, this left point of the rod doesn't really change heights at all because it's connected at that axis of rotation. It's a fixed point. However, if I look at the end of the rod here, the end of the rod maybe starts at some height h above the ground, and then that end of the rod ends at a height of 0. So that end goes through a very large change in potential energy. Well, when we look at that, and I want to say that my potential energy is mgy, which part of the y do I use? Do I use the point here that doesn't move? Or do I use the point over here that moves the whole distance? Well, actually, we don't use any of those points. We actually use the center of mass. And we describe, based on the center of mass, if this was a uniform rod, the center of mass would be dead center of the rod. And so what I do, for example, with potential energy, is we look at where the center of mass is. So I'm going to set y equals 0 to be the lowest point that the center of mass goes. So that way the height here, let's say this rod has a length of L, then this height right here would be a height of L over 2. And so I would have a y equals L over 2. So when I wanted to look at the potential energy at position 1 is going to be mg, and my y is going to be L over 2, and my potential energy at position 2 is just 0. So then you could do some sort of energy problem, and we could find the kinetic energy of this rod at this instant where it has swung down. And we would base it on the center of mass. So that's kind of an example of why we're going to bother with the center of mass right here. So what I want you to do, pause this video, go into the slides, and watch this flipping physics video on the center of mass. It's a really good example and will help kind of clarify the concepts. So when you watch that video, come back and we'll continue with this lesson. So this idea of the center of mass is very, very useful. And it can relate to our idea of rotation and axes of rotation. So in general, when we think about kind of balance, if you were to balance an object at the center of mass, then it wouldn't move. Because if you take a look, say, at this little cane here that this guy is holding, what's going to happen is we treat the gravitational force as coming from the center of mass. So say the center of mass is right here. Then we treat the gravitational force as coming from that point. So that way, if I were to say put a, like he's doing here in this video, if I were to put my hand here underneath, then my hand would create a normal force that is upwards, and then the normal force of the gravitational force would actually cancel each other out. Now, if you were to try and hold and support this thing instead of at the center of mass, but like on one end, what's going to happen is that there is a distance here, which we'll eventually call R when we start talking about torque, between the natural center of the object, and that's going to cause a rotation. And so if you try and balance an object off of its center of mass, you will end up with a rotation. So the center of mass is basically where the object would be perfectly balanced in a gravitational field. And I love this video because I actually do a lab in person where we determine the mass of a meter stick by doing something kind of cool, kind of like this. But the idea is if you take this, find some sort of object, put your fingers on either side, and if you draw them in slowly, they will balance and they will come to rest and stop exactly at the center of mass of the object. I challenge you to go and try this. And you can see that that center of this object is not dead center. It's actually closer to the heavier end on the left side of kind of the viewing screen where the handle is, because there's a little bit more mass on that end. So the center of mass is not in the center of the object in this case. Now the center of mass, if you have a symmetrical object, is going to be on the line of the axis of symmetry. So the center of mass can be inside the object or outside. So when you take a look at these different objects, with this hexagon right here, the center of mass is actually going to be dead in the center of the hexagon. When you look at this donut-looking shape, the center of mass is also in the center, but in this case, it's not actually physically in the material of the object, it's in the hole in the center. And in this crescent moon-looking shape, your center of mass, once again, is not in the center of the object at all, because the center of the object, if I've got the left end over here, the center of the object would be more like here. This is off center from that, but that's because there's more mass over on this end and less mass over here. So the center of mass is going to be closer to the larger amount of mass. So you've got this center of mass that can be in various different orientations. Now, if you have a multiple object system, you can also have a center of mass. For example, we have like a star or the sun here, and we have a planet. Now, what we've assumed so far is we've assumed that like when you're doing orbits, so say you've got the sun right here and you've got a planet moving on, we've assumed that like the sun here in the center of that is stationary. But in actuality, it's not. Both objects actually rotate around a mutual center of mass. So that center of mass is fixed, and it's actually at the center of those orbits. But the star actually traces out a circle kind of around that center of mass. And our sun is actually doing that. It's just we can't see that the sun is actually going through this wobble very much, because the center is of the sun so much more massive than anything else in the solar system that it's actually doing an orbit inside of its own object. So the center of that mass is still inside of this star, but they are both actually going through these orbits. And they're orbiting the same center of mass. Now, if you have like binary star systems, it's a little more obvious that they are both rotating around a center that's in between them, and that's because the masses of the two objects are more similar. So you could find that center of mass, and they're both going to orbit that center of mass. So how do we find the center of mass? Well, let's say we have a two-object system. The first thing we have to do is define a coordinate system. Now, how you set up that coordinate system is going to vary depending on the problem. So what we're going to do here is we're going to set up basically a one-dimensional system. We have a y-axis here defined, but it's not really necessary for our understanding because we were looking just in one dimension. So you can pick any arbitrary axis of location. So for example, what they're doing here is they're setting up a coordinate system where x equals 0 is over here on the left. So then we define different coordinates. So for example, from x equals 0, the center of this guy is at a distance of x1. And then if we look at the other one from our coordinate system, this guy's center of mass is at some position x2. Now, because these masses are not identical, the center of mass is off-center. If the two masses were exactly equal to each other, if M1 equaled M2, then the position of the center of mass would be at the midpoint. And that just makes sense. But the larger and larger mass 2 is compared to mass 1, the closer and closer the center of mass is going to get to mass 2. So how do we actually find this amount? Well, in order to actually derive the formula for the center mass, you have to use torque. We haven't learned torque yet. It's actually comes after this chapter in the text. So we're not going to really worry about how it happens now at this instant. You can definitely find videos online if you're curious. But there is a formula, and the formula works no matter what your coordinate axis is. So the formula tells us that the position of the center of mass is going to be M1 times X1. Okay, so we've got our X1 here and our M1 here, plus M2 times X2. So you've got your X2 and your M2, all divided by the total mass. So this equation could be expanded for more objects in the system. It can also be expanded to include multiple dimensions. If you have more objects, you end up with something like M3 X3 plus however many those are, and then you just continue to add the mass on the bottom. So you take the mass times the position on top, add that for every single object, making sure to always keep the same reference position. Where that reference position is, where x equals 0 is, doesn't matter. I could define x equals 0 to be here, and then I could define x1 to be that value, and then I could define x2 to be there. It doesn't really matter. But the XCM, this position that they give you, will be relative to your coordinate system. So it just kind of depends on the values. So we can actually do this. So let's assume that M1 is 1 kilogram and M2 is 3 kilograms, and we have X1 is 1 meter and X2 is 5 meters. So if we just kind of think about what's going on here, M2 is about 3 times larger than M1. So when we think about that, here's our dead center. We are not going to be there. So it's going to be about 3 times closer to M2 than it is going to be to M1. So we're going to see, based on this value, somewhere between the midpoint and where M2 is, where that's going to be. So our equation is that the position of the center of mass is going to be x1 m1 plus x2 m2 all over the total mass, which is going to be m1 plus m2. So always show your equations first, of course, and then show your numbers substituted in. So x1 is going to be 1 meter. M1 is going to be 1 kilogram. X2 is 5 meters. And M2 is 3 kilograms. Now remember that these values here for X1 and X2 are being measured assuming that X equals 0 is where that axis ends. And then this is going to be over the total mass, which is going to be 1 kilogram plus 3 kilograms. So as always, please show your numbers substituted in. Do not shortcut your work. And then if we simplify this down, you end up with 1 plus 15, which is 16 divided by 4 on the bottom, so 16. The units on top are mass meters times kilograms. Our units on the bottom are just kilograms, so the kilograms cancels. So this gives us that our position is going to be at a position of 4 centimeters. And so that XCM is going to be 4 centimeters from X equals 0. So that's going to give you your position of the center of mass. Now, if you're looking in 3 dimensions, then you have X, Y, and Z to deal with. So you can have those same equations for your XCM, YCM, and ZCM. And that center of mass could be in 3 dimensions for that. Now, what's really cool is explosions involve conservation of momentum. So when you think about your momentum, if I were to have a firework right here at the center, and let's just assume that it could just float there in space before it exploded, then I would have no momentum at the start for my system, which means I have to have no momentum at the end for my system. So what ends up happening is if you've got these particles that are moving out in one direction, they have to be particles moving in an opposite direction to cancel out. So you end up with this symmetry of this explosion where all of those particles are moving out equally in all directions. And if, like I said, if you could put that up there completely at rest so that it had no momentum, then basically all those particles would expand out and just keep moving in all those 360-degree dimensions in order for the momentum of the whole system to be constant. Now, what actually happens is gravity's acting, so you end up seeing that these particles do start to curve down in the y direction. So overall momentum is not actually conserved over time, but kind of at that first instant, you can just see that the center of mass is actually stays the same. That over time, those particles expand out, but that center of mass of that whole system remains in place. So if you're working in multiple dimensions with multiple objects, we can kind of generalize things. So we're going to use this capital M right here to represent the total mass, so you can have as many particles as you want. And then for just the position, the center of mass, using summation notation, you add up all the little mi's and xi's. So this is an mi times an xi there on top. You can do the same in the y direction and the z direction. And therefore, in vector format, you can represent the position in 3 dimensions of the center of mass, where remember that your position vector is xi hat plus yj hat plus z k hat. And that gives us our position in 3 dimensions. So if you want to be more specific, COM is usually the abbreviation. Sometimes I do CM, so you can do COM or CM for the center of mass. It just depends on the mood I'm in. CM is shorter, so I usually do that more often. But the position of the center of mass in 3 dimensions would be XCOM, YCOM, ZCOM. So you can take those formulas there or represent it all in unit vector notation. So here's an example. We have 3 particles of different masses. They form an equilateral triangle, and we want to determine the x and y components of the position of the center of mass. So if we are going through and going to solve this problem, you need to set up a coordinate system. They've done that for us here. So we're going to assume that x0 and y0 are there. So if I want to find the x component of the position of the center of mass, I'm going to need to do the x1, m1, plus x2, m2, plus x3, m3. And that has to be over m1 plus m2 plus m3. Okay, so that's going to be our general formula. So what we're going to need to do is go through and define those. So m1 is actually at a position of 0. So x0 is 0 for that one. So that simplifies things down a lot. Now looking at the second one here, if we look at kind of set up, that's 50 and 100. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4. This is at 4. So that looks like that's at a position of 140. Because I think 150 is actually that spot right there. And then M3 is coming in right here. So looks like X2 is 140, and it looks like X3 is going to be, oh, it'll be at the middle. Oh, it actually tells us, hey, that the sides are 140 long. So that's going to be at the middle there and at 70. So 140 centimeters, 70 centimeters for X3. So we can plug in XCOM is going to be X2, which is going to be 140 centimeters. M2 is 2.5 kilograms. X3 is the 70 centimeters. And M3 is 3.4 kilograms. And then you divide that by all 3 masses. So even though M1's position was actually 0, so it's not in the numerator, it is going to be here in the bottom. So we're going to have 1.2 kilograms plus 2.5 kilograms plus 3.4 kilograms, which calculates out to about 82.8 centimeters. So we've got our XCM is 82.8 centimeters. Now going through that same process in the y direction, we get YCM is going to be y1 m1 plus y2 m2 plus y3 m3 divided by m1 plus m2 plus m3. Once again, particle m1 is at 0, so y1 is 0. So when we go through, so looking at m2, so its y-coordinate is also 0. So that's kind of nice. And then for m3, its y-coordinate looks like it's going to be at the 120 centimeters. So if we go through, y2 is also 0. So our center of mass in the y is just going to be y3, which is 120 centimeters, times m3, which is 3.4 kilograms. All over the total mass, we're going to have our 1.2 kilograms plus our 2.5 kilograms plus 3.4 kilograms. And that calculates out to about 57.5 centimeters. So we have YCM is 57.5 centimeters. Now they've got that drawn here for us. So if we look, they've got, that's probably close to 83. And then that's going to be close to about 58. So the position of the center of mass is here. It's not in the center of this triangle because the masses are not all equal. If they were, it would be in the center of the triangle. So that RCOM, if we were to write that out in unit vector notation, would be 82.8 cm in the I hat direction, plus 57.5 cm in the j hat direction. So that would be our x and y components of the center of mass. And you can expand this down to 3 dimensions, but in 3 dimensions, it's harder to draw it because it's very difficult to draw things in 3 dimensions. Well, what if your object is not just a collection of point masses? Well, basically what you have to do is you have to use calculus. And this is a common method that you will use not just here for center of mass, but we will use this for rotational inertia. We'll use this method in University Physics 2 when you start looking at charge distributions. So this is a common mathematical method, and this is kind of our first introduction to it. So the idea is, let's say I have this long thin rod. So I've got this long thin rod right here. I'm going to assume that it's so thin. That it's basically just like single atoms in size. So picture that this rod was made up by individual atoms. So that you could treat each one of these little tiny pieces of this rod as a point mass. And that's essentially what we're going to be doing, but a little bit more general. All right, so there you have all of your little point masses. So what you do is you set up a coordinate system. So we're going to define right here, this is going to be x equals 0. And then we pick an example section of this rod. So I'm going to say pick this section of this rod right here. So this section of the rod, I'm going to assume has an infinitesimally small amount of mass, which I'm going to call dm. The dm, like when you were taking a rate of change, so when you do like dv dt, just one of this is an infinitesimally small amount of speed. It's a very, very, very small number. That's what we're essentially doing here. And if you remember doing in calculus, like finding like the areas and so forth, using Riemann sums, where you basically broke everything down into like rectangles and added the rectangles together. This is kind of that same process. It's going to be integration. So I'm going to assume that that section right there has a mass dm, and it is at a position of x based on my coordinate system. So therefore, the physical length or thickness, essentially, of that little piece is dx. It is an infinitesimally small portion of the overall length of this rod x. And then the end of the rod over here is x equals L. And the idea is that you treat that little tiny piece as a point mass. So if you look at this general formula here for our center mass, it basically says you add up all of the little individual mi's and xi's, so all the little tiny pieces here. Well, when you take the limit as that little bit amount of mass that you did approaches zero, it becomes an integral. So we can define our position of our center of mass is the integral from 0 to the total mass m x dm over the total mass m. But that's kind of difficult to do because in order to do that, I'd have to know what all of those little masses are. And we don't know that, but we do know where they're located. So what we do is we do a change of variables to get this equation into something that we can actually use. And we use density for this. So there are 3 different densities that we can use for objects. You're used to using volume density, which defines our volume density essentially as mass over volume. Okay, we use the Greek letter rho. That is not a P, it's a rho, it's curved like that. Okay, that's volume density. We could also define area density. That's the Greek letter sigma, and an O with a little tail on top. And that's going to be mass over area. And then we can define linear density, which is lambda, the Greek letter lambda, lowercase lambda there, as mass over length. Now, these definitions of density work for different types of objects. So most objects we would use volume density for, but if say you had like think of a piece of paper. It's very, very thin, but it has X and Y dimensions. That's where we might use something like here with the area density. Well, with this linear mass density, we use this for things that can generally be considered to be one-dimensional. So I'm going to assume that this rod is so thin, it doesn't really have a radius, it doesn't really have a width, it really just has the length. So this idea of mass over volume, mass over area, mass over length works. These formulas work assuming that the object is uniform. Uniform basically means that if I were to take any little piece, if I were to take the piece here, in order to take the piece over here, that they're going to have the exact same density. Well, this works if, say, every little piece is exactly the same. But if you had, like, say, a bat, it's not a very good bat, sorry. Drawing skills are not great. If I was to take a slice over here, there would definitely be more mass in that slice than this slice over here. So those densities aren't the same. So why am I showing you this if it doesn't work in every case? Well, what we can do is we can say, well, on a small scale, we can define like rho equal to dm over dv. And then rho can then be a function, or sigma is going to be dm over dA, or lambda is going to be dm over dx. So this is going to be useful for us because if I take a look at this lambda one here and how I've set up the dimensions for my little slice, basically lambda is the density dm dx. Well, what we can do is so that I can actually sum these up, what I have to do is I have to add up all of the little masses from the left end of the rod to the right end of the rod, which means I want to integrate in terms of x, not in terms of mass. So what I can do here is I can define dm as equaling lambda times dx. And I can create that substitution in here. And I get that my position of my center of mass is going to be the integral of x lambda dx. And then instead of integrating from 0 to m, I'm going to integrate from 0 to L. And then divide that by my total mass. And then if this rod is uniform, then lambda also equals mass over length. And so I could substitute that in 0 to L x times m over L times dx and get all over m. And then you can see what's going to end up happening here is that the mass on top here is going to cancel the mass on top there. Move this up here. So I'm going to get that my position of my center of mass is going to be the integral from 0 to L of x dx. And then I've got this L here on the denominator, so I'm going to pull that 1 over L out in front. And then this is something that I can easily integrate. So the integral of x, I'm going to get 1 over L times 1 over 2 x squared, evaluated from 0 to L. So I'm going to find that my position and my center of mass is going to be at 1 over 2L. Plug in L for x. I'm going to get L squared minus 0 squared. And the position of my center of mass is going to be L squared over 2L. So one of those L's is going to cancel. And this tells me that my position of my center of mass is L over 2. And so that tells me that the position of my center of mass is going to be dead in the center of this rod, which makes sense because we assume that the rod is uniform. So how would you solve this problem if the rod wasn't uniform? What would be different? Well, what they'll give you is they'll give you a function for lambda as a function of x. So they might give you lambda is, say, equal to 2x. In which case, we can also assume that lambda is equal to dm over dx, but we cannot assume that lambda is equal to m over L, like we did over here. We assumed that lambda was m over L and substituted that in. And the reason is because my rod would not be uniform. Because if my lambda is equal to 2x, that tells me if I pick a spot that's over here, that's further away, it's going to have a bigger density. So I'm going to have almost no density here. I'm going to get more and more dense over there. So basically each slice is giving me a bigger portion of mass. So how would this problem look? So if I was approaching this problem with a non-constant density, I do everything kind of similar. So I'm going to replace dm with lambda dx, like I would do before. So I'm going to get my position of my center of mass is going to be the integral. Once again, I'm still integrating from 0 to L of x lambda dx. And that's all over my mass m. Whereas before, I subbed in lambda is m over L. I can't do that. So I'm going to instead sub in that lambda is equal to 2x. So I'm going to get the integral from 0 to L of x times 2x dx over my total mass m. So you're going to end up here with my position of my center of mass being the integral from 0 to L of 2x squared dx over my mass m. So when I solve that integral, the 2 is a constant. And then I'm going to have 1/3 x cubed, and that gets evaluated from 0 to L over my mass m. So I'm going to get basically 2 over 3m times L cubed minus 0 cubed. And so in this case, the position of my center of mass is just going to be 2L cubed over 3M. And that's less intuitive in this case because you do have the mass in the denominator. So without knowing more numbers, it's kind of hard to see how that's going to come into play. But that's kind of gives you an example of how to do an extended object once with the rod being uniform, and then in the other case where you have a function for the linear mass density. So then bringing this back to momentum, we define that the velocity of the center of mass, and therefore like momentum and so forth, in terms of calculus, velocity is the rate of change of position. So the velocity of the center of mass is going to be the rate of change of the position of the center of mass with respect to time. So when you take that definition of the position of the center of mass, the 1 over m is a constant. And then basically you add up, instead of the MIXIs, it's just the MIBIs. So if you have a 2-object system, objects say like A and B, the velocity of the center mass is going to be like MAVA plus MBVB over the total mass. Now, if you look at this, MAVA is the momentum of object A. MBVB is the momentum of object B. Now, if I say multiply the denominator to the other side, I get MA plus MB times the velocity of the center of mass is equal to the momentum of object A plus the momentum of object B. Well, this term right here is basically the total momentum of the system. So we can basically just define the momentum of the system as the total mass times the velocity of the center of mass. And that is another definition of momentum. And so basically, if our net external force is 0, then that means that the momentum of our system is 0, which is going to tell us that if, the change in momentum of our system is 0, which tells us basically that our momentum of our system is constant. And if the momentum of our system is constant, then that means that the velocity of the center of mass has to also be constant. So if our momentum is constant, then our velocity of our center of mass must also be constant. And that's kind of cool, and you can do interesting things with that. So kind of summarizing with that, the momentum of the center of mass is the same thing as the momentum of the system. And therefore, the velocity of the center of mass is constant if the momentum of the system is constant. So think about it. You have one of those situations, like say with 2 ice skaters. And they push off of each other so that one goes this way and the other one goes the other way. Their initial velocity is 0. That is the velocity of the system. That's also the velocity of their center of mass. So what happens as the one object goes one way and the other person goes the other way, the velocity of their center of mass is 0 at the start. If momentum is conserved because they're on ice, there's no net external forces, then that means that the velocity of their center of mass must be 0 the entire time. So if they have equal masses, that means they'll move with equal velocities in opposite directions. But like if this guy has more mass, so it's 2 and 1, if this guy has more mass, he's going to have to go slower, and this guy has to go faster in order for their velocity of the center of mass to be 0 and to kind of balance out. You can do the same thing with acceleration. So you could define the acceleration of the center of mass to be the rate of change of velocity of the center of mass. And therefore, you can define that the net force is going to be just m times a when we're looking at the center of mass. So when we're looking in terms of extended objects, Newton's laws still work, but they work based on the center of mass because different parts of the object can be doing different things. So the external force on the system moves basically like a whole object, assuming that you have all the internal forces and so forth, that they are going to cancel out. So we really only have to look at the forces that are external to the system. So this comes into play. So if we take a look here at Thor tossing his hammer up and down, wherever the center mass of the hammer is, which is going to be basically right at where that, if it's well balanced, it's going to be right here. Okay, that's going to be your center mass of the hammer. Is going to be right there at the distance between the hilt and so forth. As he tosses this up and down, that center of the mass is going to go up and it is going to come down. And the center of mass is going to be governed by everything we did in 1D motion. So think about free fall. You could describe the motion of the center of mass, the position as the y position of center of mass. It goes up. It has a velocity of 0 at the top. It comes back down. The acceleration of the center of mass is going to be negative g. You could use the kinematic equations like x equals x0 plus bx0t plus 1/2 ax t squared, where you could use this in terms of the center of mass, and you can describe the motion of that hammer. And then rotation comes in for all of the other points, because as you can see, like the top of the hammer and the bottom of the hammer are spinning, so they're actually undergoing rotation, and they're rotating about that center of mass. So when we take a look at the circle, we can define S generally as arc length, and if we're looking at one rotation around the entire circle, then our circumference and our arc length are the same thing. So therefore, we can define our arc length as being 2 pi times r. So rearranging and getting 2 pi by itself, for that entire circle that you go around, you end up with 2 pi being the ratio of S to R. So this is actually our definition of our radians in terms of degrees. So 2 pi radians is 360 degrees, because the arc length that you pass through going 360 degrees is 2 pi times the radius. So whenever you were looking with theta in terms of radians, it's actually a dimensionless number, because say that our arc length was in meters and our radius was in meters, if you're dividing meters by meters, you actually get the units cancel out, and theta is actually unitless. But we didn't like this somewhere down the line, that we need to call it something so that we know what we're talking about. So that's what they defined as a radian, abbreviated short as rads. So with the radians, you have to make sure that the ratio of arc length to radius actually works even if you only go part of the way around the circle. So it works for any theta, not just 360 degrees. So this idea that theta is always S over R is actually really important, because it allows us to relate a linear quantity like arc length to the angular quantity, all based on the radius. So that the bigger the radius is, the bigger my arc length is to go through that same number of degrees. Whenever we're using any of the rotational equations from here on out, you need to make sure you're using in radians. Even if they give you values in degrees, you're going to have to convert it. So double check your calculator to make sure you're set for radians. So we're going to work with the rotation of a rigid object. So a rigid object is defined as non-deformable, which basically means it has a constant radius. So that the positions of all particles are always relative to the center of mass, and that position is constant. so that your particles can't get closer and further out. So like if you picture like tossing a pizza, the pizza is non-rigid because as you toss that pizza up, it actually gets bigger. That's the whole point. That's how they make the pizzas. Is they toss the dough, it gets faster, and it spreads out. This is not a rigid object. We're going to define our objects as rigid, which means the radius of any position is always going to be constant. This allows us to simplify our extended objects and use simpler models. In reality, things are much more complicated. There's a lot of stretch that goes on, and you have to start thinking about tensions and all sorts of things, and it gets crazy. So we're not going to have to deal with that. We're only going to deal with rigid objects. So when you look at our kinematics, we have position, velocity, and acceleration are our three main values. So we're now going to define angular position, which we use the Greek letter theta, and it has units of radians. So the position is defined based upon a reference line. So like here, you could define your reference line to be this point right here, but I could pick my reference point for theta equals 0 to be wherever I want. Usually we just, wherever the object is at its particular position, whatever the point is at the start is usually what we define as theta equals 0. So, and then you look and you assume that whatever point on that object you're looking at is going to have a radius measured from the origin or the axis of rotation, in this case the center, say, of that disk right there. And then as it rotates, it's going to move through, the point P moves through an arc length S, an angle theta. And we can use that the S is equal to R times theta to relate the arc length, the radius, and the angle. When we're looking at displacement, is going to be the difference in angular position. So if we assume that our reference line here, theta equals 0, then you're going to have, for this one, some initial theta I at point A here. And then as this thing rotates, it's going to move to some new position here at position B, which is theta F. So delta theta is going to be this angle that is the difference between those. Okay, so we assume that the counterclockwise direction is the positive direction, although kind of like what we do with linear motion, we can pick whatever direction we feel like it. So if I want left to be positive, I can have left be positive. If I want clockwise to positive, I can have clockwise be positive. But conventionally, and this agrees with what you might have done in like pre-calculus or calculus or whatever, that a counterclockwise rotation is defined as the positive direction and a clockwise direction is defined as a negative direction. We can then define our average angular velocity. Our average angular velocity is going to be the change in position over the change in time. So delta theta over delta t. And then if we take the limit as delta t approaches 0, we can get our instantaneous angular velocity, which is going to be d theta dt. So then our angular velocity at any instant doesn't have to have the average because we're looking at d theta dt. So if you were to have a graph of theta, oops, if you're going to have a graph of theta versus time, the slope of this graph would be the Greek letter omega. So omega is this curly W. It is not a W like this. It's a little curly W. It looks kind of like a butt. So it has units of radians per second because theta is measured in radians and time is measured in seconds. Please do not call that a W. You can call it omega or you can call it angular velocity. It's the lowercase omega. Capital omega is that guy. So now the direction of the angular velocity is a little weird. So the direction of the angular velocity is actually perpendicular to plane of rotation. So the angular velocity is not going to be clockwise or counterclockwise. However, a counterclockwise rotation is going to be associated with a positive angular velocity, but the angular velocity actually points perpendicular. So picture that that circle was in the plane of the screen. If you curl your fingers in the direction of rotation, your thumb points perpendicular to out or into the page, kind of depending on what you're looking at. So that is a right-hand rule. So your omega is perpendicular. So picture that you had kind of like this is a flat plane. Okay, so you're looking at your screen. So if I have my rotation is going there in that counterclockwise direction. If you were to take your right hand and put it up against whatever screen you're looking at and trace your fingers in the direction, my thumb points perpendicular out of that screen. And that's where my angular velocity vector points. And that's important because remember, like linear velocity is going to constantly change directions around the circle. So as you move around that circle, linear velocity is not constant. But your thumb always points out of the page, which we could represent with a dot. So our angular velocity is always out of the page, that no matter where I am in the circle, my thumb's always pointing out of the page. That is a constant angular velocity because it's always out of the page. So that's kind of why they do that, is so that it actually can get this idea of constant velocity. So if you change the direction of rotation so that now you're going clockwise, so if you have clockwise rotation, if you picture that my thumb is going to be pointing into the screen at that point, so that's going to be a negative angular velocity. So we can talk about angular acceleration. Angular acceleration is represented with the Greek letter alpha. That looks like this. That is not an A. It is a Greek letter alpha. And it would have units of radians per second squared. Average angular velocity would be defined as change in angular speed over change in time. If you take the limit as delta t approaches 0, this becomes a derivative, so d omega dt. So that would be your instantaneous angular velocity alpha. So the direction of alpha is also perpendicular to the plane of rotation. So remember that when we did linear acceleration, the direction of linear acceleration is in the direction of the net force. If an object is speeding up, then the linear acceleration and linear velocity are in the same direction. If an object is slowing down, they're in opposite directions. Same idea kind of works here. So for example, if I have an object moving counterclockwise, my angular velocity would be pointing up. In this case, if you curl your fingers around, my thumb's going to point up the page in that counterclockwise direction. So if I'm slowing down, then that means that my angular acceleration has to be in the opposite direction, so it would point down. If I'm going counterclockwise and speeding up, both angular velocity and angular acceleration are going to be positive, so pointing up. And then if you're going counterclockwise and slowing down, your angular velocity is going to be down, so it's going to be negative, but your angular acceleration is going to be positive because you're slowing, so they have to be opposite. And then if you're going clockwise and speeding up, they both have to be in the same direction. In this case, they will both be negative. So in terms of rotational kinematics, basically everything that we've done is nearly identical in terms of linear kinematics. So when we looked at our average velocity, that's change in linear position over change in time. Our average angular velocity is change in angular position over change in time. So if we have constant angular acceleration, then we can describe our kinematic variables using the kinematic equations. Otherwise, we have to use the differential versions. So they look exactly the same. You just replace your variables. So if we have our kinematic equations, we'll have constant angular acceleration, and you can derive these with respect to time. So if you take your angular velocity as the integral of alpha dt, you get omega I plus alpha t. So this is equivalent to our v equals v0 plus a times t. You can do the same by taking that equation, integrating with respect to time. And so this gives us that theta is our initial theta plus our initial velocity times time plus 1/2 alpha t squared. This is equivalent to x equals x0 plus bx0 t plus 1/2 a x t squared. So they have the exact same form. all you have to do is just then substitute the symbols. So I give you some of those on the formula sheet, but you can always just take what you have and go. So these are the four main linear equations. So these are the main three. This is a fourth one that I remember way back when saying, hey, this is going to have memorized because it doesn't have acceleration in it, but it's not something that you're given. So these are those exact same equations over here. You can see all you have to do is just replace the variables. It's pretty handy. So if I was to have a graph of angular velocity versus time, this would give me that my slope is going to be angular acceleration and so forth. So everything that you did is going to work. If I had that angular velocity versus time, and I found, say, the area under the curve, that area is going to be equal to my displacement. So all the things that you did before are going to work here. So just kind of looking at an example, a wheel rotates with a constant angular acceleration. If the angular speed of the wheel is 2 radians per second at t equals 0, through what angle does the wheel rotate? And then what's the angular speed? So looking at our kinematic equations, you're going to have to start going back and think about, well, what do I know? What don't I know? So at t equals 0, it's going to start with 2.0 radians per second. So they're giving us essentially omega 0. And then they're giving us our alpha here. And we want to know what angle does it rotate. So we're looking essentially through for delta theta. So I need omega 0, alpha t, and delta theta. I'm also given times. So I'm going to probably use that theta is equal to theta 0 plus omega 0 t plus 1/2 alpha t squared. I'm going to assume that I start off at a position of 0. So I can find theta. And then I have omega 0 t plus 1/2 alpha t squared. So I can plug in my numbers. Omega 0 is going to be the 2.0 radians per second. Notice they didn't give me what direction it's rotating, so I'm just going to assume that whatever direction it is the positive direction. I'm looking at 2 seconds, so my time is 2.0 seconds, plus 1/2 alpha is 3.5 radians per second squared. And then my time is 2.0 seconds, and I square that. So I can find that my theta is going to be 11 radians. And I use just 2 significant figures for this one. So it'll have gone through 11 radians. So remember that pi is 3.14 radians. So this has gone a little over 3 times around the circle because we haven't gotten to the 4th, which would be 12 radians or so. So then the next part, it says, okay, what is the angular speed of the wheel at 2.0 seconds? So I can use a kinematic equation like omega equals omega 0 plus alpha t. So I can just plug in omega 0 is going to be my 2.0 radians per second. My alpha is 3.5 radians per second squared. Ran out of room. So I just need to multiply by that 2.0 seconds. Sorry for that. So when you do 2 plus 3.5 times 2, you get an angular speed of 9.0 radians per second. So you use these kinematic equations very similar to what we do the linear ones. Now, how do those linear and angular quantities relate? Well, every point on the circle has the exact same angular velocity. So you can see that each point is going through the same delta theta and the same delta t. So omega is the same for all of them. But you can see that the blue one out here on the edge has to go through a much larger linear distance than the red one in the center in any one time. So while they all have the same angular velocity, they do not have the same linear velocity. So we can pull up a simulation for this. So here's a fun little simulation. We can give the little bug here a little angular velocity. And so you can see that we have some linear quantities shown here. We have the linear velocity, which is tangent to the radius, which we're used to. And then if I put another ladybug on, put them at a little further radius right here. So you can see that although they are traveling at the exact same angular velocity, that the green bug, because it has a larger radius, actually has a larger linear velocity. And it also has a larger linear acceleration, centripetal acceleration, kind of which we saw before. This is a fun little simulation that you can use for lots of different things. So I play around with it. Looking again at kind of our linear motion and relating our linear motion, we define our tangential velocity, v sub t, in meters per second. So we did talk about this tangential velocity before when we did circular motion. So it's always tangent to the radius. So there's a 90-degree angle between the radius and the velocity vector. Its magnitude is the linear distance traveled in time t. So it's going to travel a linear distance of the arc length in time delta t. So if you sub in that our arc length is going to be r times delta theta, then you end up with the r times delta theta over delta t. You can rearrange that and get delta t over delta t, which is the same thing as omega. So we can define, therefore, that our linear speed, which is tangent to the circle, vt, is equal to r times omega. So the faster you're rotating, the faster the tangential speed, but also the further you are away from the center, then you're going to have a larger tangential speed. And if you're at the center, so if you're at a point that is at the origin, you have no linear speed because you are not having a linear displacement. Additionally, we talked about centripetal acceleration, so just kind of some reminders here with centripetal acceleration. Centripetal acceleration, AC, also called radial acceleration, is in meters per second squared. It is the component of the acceleration that points towards the center of the circle that is responsible for changing the direction of the velocity. So if you're going at a constant speed around the circle, then the only acceleration you have is a centripetal acceleration. So we know that our centripetal acceleration is v squared over r. In this case, it's a tangential speed. Our tangential speed we just defined as r times omega. So you can plug in r times omega into our definition of centripetal acceleration. One of the r's is going to cancel, so you get your centripetal acceleration is r times omega squared. So you can find the centripetal acceleration by knowing the angular speed and the radius. The angular speed is going to make a big difference, though, with the centripetal acceleration, kind of like the linear speed makes a big difference with the centripetal acceleration. Now, that was if we were doing uniform circular motion. If it's non-uniform, you could be changing speeds around the circle. We weren't able to solve problems really like that before. So that's because you can also have a tangential component of your acceleration. So that tangential component of the acceleration is tangent to the circle, and it's responsible for changes in the magnitude of the linear velocity. So centripetal acceleration is responsible for changing directions. The tangential acceleration is responsible for changing speeds. So we define the tangential acceleration as the change in tangential speed over time. Once again, we can define Vt is equal to r omega, so we can substitute that in up top here. And then because the radius is assumed to be constant, we can pull it out in front, and then you get delta omega over delta t, which is our definition of alpha. So our tangential acceleration is r times our angular acceleration. So there's a difference here in the way that you're behaving, because your tangential acceleration is based on your angular acceleration. If you're going at a constant speed around the circle, then you have no angular acceleration, which means you have no tangential acceleration, but you would still have a centripetal acceleration if you were moving in a circle. So we now have lots of different types of acceleration. You have angular acceleration, alpha. You have tangential acceleration, centripetal acceleration. But what if I just say acceleration? If I just ask you for acceleration, I'm asking you for the vector sum of the linear acceleration. In that case, you would use the Pythagorean theorem to find that acceleration. So it can get very, very confusing very quickly when you're talking about these acceleration values. So some reminders. They have to say angular or rotational when referring to position, velocity, or acceleration. If it just says velocity or it just says acceleration, it's talking about the linear quantity, even if you're in the rotation unit. We assume that all points on the object are going to have the same angular velocity, but different points will have different tangential velocities depending on the radius. But the further away you are from the axis of rotation, the higher that tangential velocity is. We assume that they all have the exact same angular acceleration, but the further away your radius is, the larger it's going to be, because we know that our s is equal to r times theta. We know that our tangential speed is r times omega, and our tangential acceleration is r times alpha. So you notice those have a nice pattern there between our linear and our angular values. So the tangential quantities depend on radius. The angular velocities, accelerations, and so forth do not. So let's take a look at one example. We have a discus thrower moving the discus in a circle with a radius of 80 centimeters. At some instant, we have an angular velocity at that instant, and our speed's increasing. So we have an angular acceleration that are going to be in the same direction. And we want to find the tangential and centripetal components of the acceleration and the magnitude of the acceleration. So what we're going to be looking at is we're going to look at that our tangential acceleration is equal to r times alpha. Our centripetal acceleration is v squared over r, or r omega squared, and that v is our tangential speed. And then our linear acceleration is the square root of ac squared plus at squared. So when we're looking at our tangential acceleration, our radius is 80 centimeters. Our angular acceleration is 50.0 radians per second squared, which if you plug that in gives you a tangential acceleration of 4,000. I need that zero to be significant. And that would be in centimeters per second squared. So when you look at these units, just one thing to be careful of. Notice that we're taking centimeters times radians divided by seconds squared. So what happened to the radians here in my unit? Like I mentioned earlier, radians is literally a placeholder unit. It doesn't exist. So anytime you're doing multiplication with linear variables, the radians just kind of goes away. We don't write it down because it's just a placeholder for that dimensionless angle unit. So we have our tangential acceleration is 4,000 centimeters per second squared. Our centripetal acceleration, we're going to use the r omega version. Our radius is 80.0 centimeters. And our angular speed is 10.0 radians per second. And we square that. So that's going to give us 8,000. And that's going to be centimeters per second squared. And it's that third one there. That's the significant one. So then to find our linear acceleration, we would do AC squared. ACs are 8,000 centimeters per second squared. Square that plus our 4,000 centimeters per second squared. And it gives us to three significant figures, 8,940 centimeters per second squared. So we have lots of different types of accelerations that we could work at. We have our angular acceleration, tangential acceleration, centripetal acceleration, and then just acceleration. So that's what we have for today. This was a lot. I know theoretically, especially with the center of mass stuff, there's a lot going on. These are some good videos on how to work with center of mass. This one's really good for using that differential equation, breaking it up into pieces and then integrating in order to find center of mass. And then these are some good videos on just kind of the rotational kinematics. This one is my video. I walk through kind of everything that I did before, but with a little bit more detail. And of course, the crash courses are good, but they're kind of a little overwhelming. But they're a good kind of just kind of refresh your brain.